The closed die forging process of eye bolts begins with cutting a steel bar to length and heating it to forging temperature. The hot billet is then placed in the first die, where it is roughly shaped using a mechanical press. In the second die, the part undergoes a block forging process, where it is more precisely shaped and punched to create holes in the eyepiece. This combined shaping and punching process ensures alignment and reduces subsequent machining. Next, the part is transferred to the final die, where it receives a detailed shape with precise contours and dimensions. The overhang created during the forging process is then trimmed off using a specialized cutting die. The forged part is then cooled to reduce its temperature through water, and the worker continues to forge it back and forth to ensure strength. Finally, the worker rivets and uses a grinder to complete the process to ensure the bolt has the correct shape. The process begins by placing the electric motor stator into the Anger 3 machine. A hydraulic blade cuts through the outer shell, exposing the copper windings inside. The stator is then rotated and cut again to ensure full access to the copper. Once the casing is opened, a pusher system forces the copper windings out of the stator slots. The separated copper is collected for recycling, while the remaining steel parts are removed. This efficient process handles stators from 40 to 460 millimeters in diameter, making it ideal for small and medium-sized recycling facilities seeking safe copper recovery. A hydraulic press punches a hole in the main body, then extrudes the branch using high pressure. The form T is trimmed precisely by cutting machines to achieve the final T shape before further processing. The 1000 weight and 3500 weight hammers deliver fast, repeated blows to shape small to medium billets. The 500-ton press forges larger sections with steady force, enhancing density. The 1,200-ton press handles massive components, applying deep, controlled pressure for refined grain structure and improved mechanical properties in critical forged parts. The D52 ring rolling process begins with the loading of the preheated ring blank onto the shaft. The main shaft slowly presses the blank onto the shaft, while the rollers ensure a uniform height. As the ring rotates, it expands radially and reduces in thickness. The operator monitors and adjusts the process in real time. When the desired diameter and shape are achieved, the finished ring is unrolled. This process ensures material efficiency in ring production. Preformed windings rapidly designs coils from a production database, then precisely loops copper wire up to 9 meters using automated machines. Coils are shaped with computer-controlled forming equipment, insulated with resin systems, tested rigorously for quality, and quickly packaged. This streamlined process delivers high-quality coils within days, not weeks. The precision machining process of helical components begins with milling operations using a cutting head equipped with an additional axis of movement. This extra degree of freedom enables complex geometries to be accurately shaped during the finish milling process. The milling phase ensures the near-net shape of the component before grinding. Subsequently, grinding is performed with a profile that has been altered for micron-level accuracy. The grinding wheels are carefully profiled using high-precision wheel profiling techniques, employing dressable abrasive materials such as aluminum oxide and cubic boron nitride. These dressable wheels allow for repeated conditioning, ensuring consistent dimensional accuracy and surface finish throughout production. The machine setup supports flexible tooling options and offers a variety of chucking configurations to accommodate components up to 420 mm in diameter and 2.2 meters in length. The machine is designed for heavy-duty operation with high power to remove stock efficiently, supported by a 900 mm diameter swing and a 4.5 meters length capacity. After the machining process, comprehensive after-sales service, including machine reconditioning and rebuilding, guarantees long-term operational precision and reliability. This process is essential for manufacturing ultra-precision helical components used in air and refrigeration compression sectors, meeting stringent industry standards for quality and performance. The automated tube manufacturing process begins with the loading of raw steel coils into an uncoiler, which uncoils the steel coils at regular intervals onto the production line. The strip passes through a leveling system, where rollers flatten the strip to ensure uniformity and eliminate any bends or stresses. The flattened strip is then fed into the forming section, where a series of precisely engineered rollers gradually shape the strip into a cylindrical shape. Each roller incrementally bends the strip, ensuring a smooth transition from flat to tubular without compromising the integrity of the material. The edges of the formed strip are carefully aligned in preparation for welding. A high-frequency welder fuses the edges together, creating a continuous tube with a strong seam. The welding process is closely monitored to ensure a consistent, defect-free joint. The newly welded tube then enters the cooling system, where a controlled flow of water and air reduces the temperature of the tube, stabilizing the structure and preventing thermal deformation. After cooling, an automatic cutter equipped with a high-precision blade cuts the tube to the specified length. The cutting process is synchronized with the line speed to ensure accuracy and clean edges, preparing the tubes for further processing. The structural steel fabrication process begins with positioning the 16 IPE 400 wide flange beam into the FICEP drill system equipped with sub-axis positioning. This advanced machine features 3 fully independent spindles that can simultaneously drill both flanges and the web of the beam. Each flange receives 20 holes with a 20 mm diameter, while the web is drilled with 20 holes of 18 mm diameter. The holes are offset by 5 mm between the flanges and the web. Thanks to the sub-spindle positioning, all 60 offset holes are drilled in just 76 seconds. This rapid operation is made possible because each spindle operates independently, maintaining maximum productivity and precision without repositioning the beam. Simultaneously, the machine performs scribing on both flanges and the web. Unlike fixed spindle drill lines, which can scribe only one surface at a time, this system scribes all 3 surfaces concurrently. Furthermore, when the optional underside scribing feature is enabled, The system can scribe 4 surfaces at once. This simultaneous multi-surface scribing significantly enhances fabrication speed and accuracy, reduces manual layout work, and streamlining downstream assembly. The process starts by reheating the steel slab to 1,330 degrees Celsius. In the plate line, the slab is reduced through 2 reversible mills in several passes to the desired thickness and width. It is then cooled, straightened, and cut. In the strip line, the slab is first reduced to 2 inches in a universal reversible mill, then to 1 inch in the M-stand. Final thickness is achieved in a 6-stand rolling mill. The strip is cooled and coiled as a hot rolled coil. For cold rolling, pickling removes oxides using hydrochloric acid. The strip is then reduced at room temperature, annealed at up to 750 degrees Celsius, and temper-rolled to improve surface quality and hardness. The crankshaft machining process on the Behringer VDF 221-226 CX and VDF 221 CIM is a high-precision, multi-stage operation optimized for series production. The process begins with the automatic loading of the raw crankshaft into the machine using a gantry loader, ensuring efficient component transport and minimal downtime. The first operation, turn, is performed on the VDFCB module. This operation consists of simultaneous turning and turning of the crankshaft main bearing and pin, using high-speed cutting tools to remove material and achieve precise dimensional tolerances, typically within plus or minus 0.01 millimeters, ensuring optimal concentricity and surface integrity. Next, the workpiece is transferred to the VDFCM for external milling operations. This module uses advanced milling cutters to machine the crankshaft pins and counterweights, achieving smooth contours and precise geometry, which is critical for dynamic balance and performance. The milling process maintains surface roughness values below 0.8 micrometers, enhancing fatigue resistance. Internal milling of the main and pin bearings is then performed on the VDF 221 CIM, using dedicated cutters designed for vibration-free operation. This step ensures precise bearing shaft diameters and high-quality surface finishes, with roundness tolerances within 0.005 millimeters. The process continues with turning operations on the VDFCT, where carbide inserts refine the crankshaft surfaces, including the thrust and crankshaft faces, to meet strict dimensional and geometric specifications. Finally, roller polishing is applied to the machined surfaces, using high-pressure rollers to create compressive stress, improving surface hardness, and achieving a mirror-like finish. This enhances durability and wear resistance. The modular design and compact layout of VDF machines optimize workflow, ensuring high throughput while maintaining precision in every operation, making them ideal for large-scale crankshaft production. The assembly of the Terex Demag CC8800-1 crawler crane begins with unloading major components, including the tracks, base body, and boom sections. The superstructure is placed on the tracked undercarriage using auxiliary cranes. Next, counterweights are added to the rear to ensure stability. The main boom is assembled on the ground by joining individual lattice sections. Hydraulic pins secure each connection. The boom is then raised gradually using the crane's own lifting system, assisted by support cranes. The superlift counterweight tray and mast are assembled and connected behind the crane. Cables and pendants are installed to balance the boom. Once the main boom and superlift are fully erected, functional tests are conducted to verify movement and control. The final configuration includes a long main boom and superlift system, ready for heavy lifting operations. The entire process is carefully synchronized to ensure safety and precision throughout the assembly. The metal casting process begins with the fabrication of a precise pattern, typically crafted from metal, replicating the final component's geometry. This pattern is embedded in a sand mixture, often silica-based with binders, to form a mold. The sand is compacted around the pattern using a molding machine or manual ramming to ensure dimensional accuracy. After compaction, the pattern is carefully extracted, leaving a cavity that mirrors the component's shape. Molten metal, such as steel, aluminum, or iron, is prepared in a high-temperature furnace, typically an electric arc or induction furnace, reaching temperatures exceeding 1,500 degrees Celsius for steel. The molten metal is refined to remove impurities, ensuring optimal flow and material properties. It is then transferred via a ladle and poured into the mold through a sprue, a vertical channel connected to runners and gates that distribute the metal evenly, minimizing turbulence and preventing air entrapment. The mold, often incorporating cores for internal cavities, allows the molten metal to fill the cavity completely. Cooling follows, with solidification time dependent on the alloy's thermal properties and the casting size, ranging from minutes to hours. Controlled cooling prevents internal stresses or defects, like shrinkage porosity. Once solidified, the mold is broken, using vibration or mechanical means, revealing the raw casting. Sand is removed through shaking or shot blasting, and excess material, such as sprues and risers, is cut off using saws or torches. The casting undergoes surface cleaning via abrasive blasting or chemical treatment to eliminate scale and residual sand. Final inspection involves non-destructive testing, such as ultrasonic methods, to detect internal flaws. Dimensional checks ensure compliance with tolerances. The casting is then machined or heat-treated as needed for its intended application. The hot drilling process involves the steps of creating a new branch on an existing pipeline without interrupting the flow. The process begins with careful preparation of the equipment and work area. Workers use a grinder to grind away the oxidized pipe surfaces. The exact drilling location is marked on the pipe surface using precise measurements to ensure alignment with engineering specifications. A flange, usually a weld-on fitting, is fastened to the pipe at the marked location using welding and grinding. Workers paint and retest the newly installed section of pipe. A valve, usually a gate or ball valve, is then installed to the flange, creating a sealed interface that maintains the pressure integrity of the pipeline. This assembly ensures a stable foundation for the subsequent drilling operation. Next, the hot drilling machine is installed. It is equipped with a specialized cutting tool, which is bolted or clamped to the valve. A pressure-resistant sealing mechanism, typically involving a gasket or O-ring, is used to prevent gas or fluid leakage during drilling. The sealing system is rigorously tested to confirm that it can withstand the pressure inside the pipeline, which can range from low to several hundred psi, depending on the application. This step is critical to operator safety and environmental protection. The drilling phase begins with the hot drill activating a cutting tool, typically a hole saw or annular cutter. The cutter rotates at a controlled speed, penetrating the pipe wall while the pipe remains under maximum operating pressure. The cut metal is retained inside the drill to prevent it from entering the pipeline and causing blockages or damage. The machine's feed mechanism ensures a steady, accurate cut, maintaining the structural integrity of the pipeline. Once the cut is complete, the drill bit and cutter are retracted into the hot drill chamber. The valve is closed to isolate the newly created branch, and the drilling equipment is carefully removed from the valve. The pipeline now has a working branch, ready for additional accessories such as new piping or measuring equipment to be attached. This process is performed with high precision, allowing for expansion or maintenance of the system without stopping operations, ensuring continuous flow and minimizing downtime. The entire operation adheres to strict technical and safety standards to ensure reliability and efficiency. Aluminum ingots are hot-rolled into strips, reduced further in a tandem cold mill, and processed in a single-stand cold mill. Automotive strips undergo annealing, cooling, and chemical coating. The line includes heat treatment, flatness control, and high automation for premium product quality. The titanium shoulder implant is precisely machined on the NTX 1000 using simultaneous 5-axis turning and milling. The process begins with securing the titanium bar stock, which is then rotated and shaped using the high-speed Capto C5 spindle. The B-axis, with a 240 degrees rotation range, enables complex contouring from multiple angles. Milling operations follow, involving all 6 faces of the part. The X, Y, and Z axes provide full accessibility, while thermal control ensures dimensional stability. Fine features and cavities are created using high-speed tools at up to 12,000 revolutions per minute. The machine's high rigidity and linear guides contribute to smooth, accurate cuts. An integrated in-machine robot handles part repositioning and unloading, ensuring continuous and efficient processing. The result is a finished implant meeting strict medical standards, all completed within a single setup for optimal precision and throughput. The production of aircraft carrier chains is a highly specialized process that requires strength and consistency. These chains consist of multiple ring components, each of which is formed by assembling 2 C-shaped components. This design improves the mechanical performance of the chain, especially in terms of tensile strength and resistance to surface cracking during heat treatment. The process begins with the forging of the C-shaped components. High-quality steel bars are heated in an industrial furnace until they reach a red-hot state. The bars are then fed into dies, and forged under high pressure to create the C-shaped components. This forging step not only creates the basic shape, but also improves the internal grain structure of the metal, enhancing its mechanical properties. After forging, the components are sent to cutting and punching stations. Excess material is trimmed off, and precision holes are punched at both ends of each C-shaped piece. These holes are required for the final assembly, where screws will be used to join the two halves together. The punching process must be precise, as any misalignment will affect the fit and strength of the final ring component. The cut C-shaped components then move on to the machining stage, where their internal surfaces and contact areas are carefully shaped. Each component is equipped with a series of projections and corresponding recesses, which help align the two halves during assembly. The design also includes a projection that is slightly smaller than the clearance length on one half, allowing it to fit into the groove of the other half. On both sides of this projection, threaded screw holes are drilled to align with the through holes on the opposite half. After machining, the ring element assembly begins. A previously completed chain ring is inserted into the slot of a C-section. The second C-section is then aligned and mated to the first. The protrusions and recesses fit together for precise positioning. Screws are inserted through the aligned holes and tightened into the threaded holes. This method ensures a strong, permanent connection without relying on welding or riveting, both of which can weaken the surface and internal structure. After assembly, the ring element is sent to the heat treatment department. The main goal here is to achieve a hard surface while maintaining a hard and flexible core. The components undergo a surface hardening treatment, such as carburizing or induction heating. This significantly increases the wear resistance and tensile strength of the links, which is important when carrying heavy loads. After surface hardening, the parts are subjected to a quenching process, where they are rapidly cooled in a controlled environment such as oil or a polymer bath. This process locks in the hardness achieved in the previous step. To reduce internal stresses and prevent brittleness, the links are then tempered by reheating to a moderate temperature and then quenched again. After heat treatment, the assembled links are quality inspected. Each link undergoes dimensional inspections and non-destructive testing methods, such as ultrasonic testing or magnetic particle inspection, to detect internal or surface defects. This ensures that only links that meet strict mechanical and safety standards are passed on to the next step. Once approved, the surface of each link is cleaned by shot blasting to remove oxidation and heat deposits. This step prepares the chain for an optional anti-corrosion coating, which may include painting or galvanizing, depending on the operating environment. After surface treatment, The finished ring components are assembled into a continuous chain. A technician inserts a new ring through the gap of the previous ring before bolting the new link together. This creates a link structure that distributes the load evenly across all links. The assembled chain is then subjected to simulated load testing to verify its strength and structural integrity. This advanced chain design offers several advantages. Traditional welded or riveted chain rings can suffer from weak spots where thermal stress cracks can develop. In contrast, this bolted double C-member structure avoids these risks. It also allows for more efficient and uniform surface heat treatment, improving strength without sacrificing ductility. The result is a high-performance chain that is reliable in the harsh operating conditions of an aircraft carrier. In summary, the manufacturing process of aircraft carrier chains involves a combination of precision forging, machining, mechanical assembly, heat treatment, and quality control. The use of bolted C-sections rather than welded improves structural performance and reduces failure rates, making these chains suitable for the harshest marine environments and heaviest lifting tasks.